Good morning. Thank you for joining us for the IGSHPA September Town Hall. I'm Jeff Hammond, the Executive Director at International Ground Source Heat Pump Association. I have just a few announcements to make before we turn this over to our speaker. We're lucky to have one of our board members this morning, Brian Urlaub of Salas O'Brien. Excited about his presentation, but I wanted to just give you a few updates. A lot going on at IGSHPA right now. So we'll just go through some slides here with the latest IGSHPA news. On this town hall and our Dig Deeper webinars, we have a lot of great presenters, and we're already starting to get presenters for 2024. If you're interested in presenting at one of the town halls or Dig Deepers, town halls are a little broader topics, Dig Deepers are a little more technical. Just contact info@igshpa.org and submit your abstract. Also, we have one opportunity for sponsorship for a town hall this year, and we have some open for 2024. I think about 6 or so. So if you want to get your name out there, it's a great way to do it. These town halls and Dig Deepers are recorded. So if you're sponsoring one of these events, your logo stays on that recording for as long as YouTube will have us. Updates on the 2023 conference. It sounds like it's far away, but December will be here before we know it. And you don't want to miss that early bird special pricing. It ends November 3rd. So make sure you go to igshpa.org and register for the conference, or you can read more about the conference at igshpa.org and go to the 2023 conference page. We are thrilled to have all of our sponsorships filled early this year. So every one of the spots are filled. We certainly couldn't do the conference without our sponsors, and we really appreciate their dedication to IGSHPA. We just filled our diamond sponsorship last week, so everything is in order, and we hope you'll visit our sponsors' websites to learn more about them. We look forward to seeing them at the conferences. The conference exhibit hall is filling up quickly as well. This list keeps getting larger each time I do a town hall or Dig Deeper overview. And you can see here from the map, we have some booth spaces left, but they are going quickly, and the opportunity to combine spaces is a bit limited now. So if you want a 10 by 20, you'll want to jump on pretty quick so you can combine some of these. You could also combine all 4 of these booths here. And we may be able to do some other organization if you're looking for a 20 by 20. The entrance to the hall is right over here. The NGWA booths are just right across this aisle here. So this is a great location, and now's the time to reserve your space if you haven't already. Program guide advertising is also filling up quickly. I think we have most of our full page ads already full, and a lot of half-page ads already. There's still quite a few quarter page left. The inside front cover is left, as is the back cover. So if you're looking at advertising in the program guide, you'll want to check that out here pretty quickly at igshpa.org. Conference agenda is online in the conference page at igshpa.org. We have a lot going on. We're thrilled to have our keynote speaker from the Department of Energy's Energy Efficiency and Renewable Division. Alejandro Moreno is acting secretary there, so we're really expecting a great keynote speaker at the conference. If you haven't checked out the awards, we're going to be awarding a residential innovation, a commercial innovation, and 3 award of excellence at the conference this year. Voting started this week. If you haven't seen that in your email inbox, you'll want to check that out. It does end at the end of this month. And you'll find a link to the voting on the 2023 conference page. Please note that voting is only for members. And so if you aren't a member or you need to renew your membership, you'll want to do that before the end of September so that you can vote for these incredible awards. There's a lot going on. And when you go to that page, you'll find all of the nominees listed. Same holds true for our board of directors. IGSHPA members can vote for board of directors. We have 4 open seats right now, and we are still taking nominees until the end of September. Voting will start around mid-October. The open seats for the IGSHPA board of directors is the architect engineer sector. the ground heat exchanger installer sector, and we're adding 2 new board members this fall, a manufacturer sector as well as a utility sector. So that'll bring the board from 5 to 7. And if that's something that you're interested in, you'll need to get your nomination in by the end of September. Please send an email to IGSHPA.org. If you're interested, we'll just need a bio and a photo, and then you'll be able to run for the board of directors. We appreciate all of the interest so far. Our next research conference is in Montreal in May of 2024. If you'd like to present an abstract, those are being accepted through next week, September 18th. And so you'll want to get those in pretty quickly if that's something that you're interested in. If you haven't been to our website lately, there's a brand new layout at IGSHPA.org, and it should be much, much easier to navigate. Hopefully it's easier to find things. It continues to be updated, so this isn't the final iteration, but hopefully it's a little bit easier to use. We are really excited about bringing in Geo Outlook magazine back. The first edition will come out at the end of this month, so watch your inbox for that. It is also going to BNP Media subscribers. So we are expecting to get quite a lot of traction out of Geo Outlook. We're starting out with 2 editions at first. We'll have another one after the September edition in January and July, and hoping to move to quarterly after that. So watch out for that Geo Outlook. Some pretty cool things happening there. If you're looking for CEUs from these webinars, just make sure you send in the chat your name and your email address, and we'll keep track of those for you. So if you need CEUs for your IGSHPA certifications, this is a great way to get those by attending these Dig Deeper and town hall sessions. If you for some reason have colleagues who are not able to make this particular session, they can watch later on our YouTube channel. As long as they use this code, they'll get credit for watching the town hall later on. You don't need this code today if you're attending live. Just simply send us your name and email address. But if you have colleagues who would like to take advantage of the CEUs, have them go to our IGSHPA YouTube page, enter this code, and then they'll get credit for it by sending that information to IGSHPA.org. All right, just a few housekeeping things. If you would, please enter any questions into the chat, and I will read those at the end of Brian's presentation. Hopefully we'll get to all those questions, but if we don't, we'll follow up later on. Also, please mute your microphone unless you're speaking, and we will be recording this session for viewing later on. Usually it takes a day or 2 to get uploaded to the IGSHPA website. If you go to the website and look under publications menu, you'll find town hall recordings under there, and they're also on the IGSHPA YouTube channel. All right, one more item before I turn this over to Brian. Just a quick disclaimer and potential conflict of interest. The upcoming presentation represents the opinion of the presenter and does not represent any official position, opinion, or endorsement of any products or services by IGSHPA or its members. IGSHPA town halls and Dig Deeper webinars are for member updates and education on the latest information in the geothermal heat pump industry and are not meant to endorse one technology or brand over another. It is the presenter's responsibility to disclose any conflict of interest or position that may arise in the content of the webinar. So with that, I'm happy to introduce Brian Urlaub. As I mentioned, he's on our board of directors, and we're pleased to have him today. Brian is the Associate Vice President and Director of Geothermal Operations at Salas O'Brien. He's involved with all aspects of the projects from procurement to design, project management, and commissioning. He graduated in 1993 with an associate degree in HVAC technology and design from Chippewa Valley Technical College in Eau Claire, Wisconsin. Mr. Urlaub started out his career in the field, installing and servicing all different types of HVAC systems. In 1996, he moved to inside sales and design and was introduced to his first IGSHPA geothermal course. He has been dedicated solely to the geothermal industry since 1999. His current job as Director of Geothermal Operations includes such duties as working with mechanical engineers on energy efficient designs, mechanical contractors on installations, drilling contractors on geothermal loop field installations, and architects on better understanding of geothermal technology and implementation of innovative geothermal systems. He's been a member of IGSHPA since 1997, past president of the Wisconsin Geothermal Association, past board of directors of the Minnesota Geothermal Heat Pump Association, and past advisory council member of IGSHPA. His certifications include IGSHPA accredited installer, IGSHPA certified geo exchange designer, IGSHPA certified trainer, and IGSHPA CGD plus trainer. Lots of IGSHPAs in there, which is a good thing. So thanks for joining us, Brian, and I'll turn it over to you.
Yeah, thanks, Jeff. I guess I maybe should have shortened that bio up a little. That was a little much. But anyway, appreciate it. Glad to be here. Looking forward to talking a little bit about the next generation of geothermal and what we're kind of seeing in the marketplace. And, just this is going to be a little high level of really some design steps, if you will, looking at, what's maybe the process of looking into a lot of this newer technology and what we call 5G district or community systems. And we'll also talk a little bit about single building innovation as well. So with that, let's see if I can. So why are we here? First reason, I think we're all aware of the decarbonization, electrification movement happening across North America. And that's really pushing the envelope of standard practices and what we're used to in this industry, that, kind of the same old design methods and practices we've seen for the last, 3 decades or so. Especially when you start moving into the urban environments, which is what I'm going to show a lot of today in some project profiles, is really about, we have all these large cities. How do we possibly decarbonize and electrify these cities with geothermal heat pumps? Mainly because we don't have a lot of space to work with, right? So what are we going to do as far as, molding that technology with other technologies to really get to a full electrified solution that doesn't really impact the grid negatively? So, that's also, what we're going to talk about, not just single buildings, but we're also going to look at some campuses on the district side and communities. We're both seeing from the residential side in district geothermal in communities. We're also seeing this from both private and public campuses, higher education, and then of course the private campuses. So how do we electrify these campuses, get them off of traditional gas and fossil fuels and steam technologies to using geothermal, along with a host of other technologies, to really make the biggest impact that we can, as far as low peak demands on the grid and high efficiency. So that's why we need multi sources of thermal energy. That's really the key to all of this, is looking at a site and going, okay, it's not just geothermal heat pumps and vertical ground loops. What other thermal assets are on site? What else can we use? Those have obviously major capital cost implications. There's always space constraints or restraints, for any particular site. Okay. And then, of course, again, I've mentioned the electrical grid. What are we going to do to make sure that if we put all this, equipment on the electrical side, that we're now not impacting that grid to where we cannot, provide the power, and we have either brownouts or, they have to put major infrastructure costs into upgrading, transmission lines, power generation. So those are all really key components as we decarbonize, the country. So 5G actually came from NREL. 5G is I know we all think of cell phones, but 5G is just 5th generation, if you will. And this is just kind of adopting old ways with new ways to thermal energy. District energy has been around for centuries. Hot water and steam systems in Europe and all over the world have been piped underground in serving, cities and communities for centuries. The issue with that is it was, generated through fossil fuels, almost always. And then, of course, it was a one-way thermal movement. We only put thermal one direction. We didn't have any thermal sharing, and we didn't, connect buildings in a way that we can actually leverage that diversity between buildings. It was always just a one-direction highway of thermal energy. And then, of course, from single buildings, in the past, for decades with this technology, it's generally been, we have a single source geothermal loop of some kind, whether it's a vertical, ground loop or a pond loop, whatever it might be, connected to one building. And you may have distributed heat pumps, or you may have a little central plant. But in the past, it was a single source and it was a single building, whether it was residential or commercial. And so things are kind of changing in a way that we're taking that old district energy, model. We're bringing in, geothermal technology, and now we're looking at a byway of thermal energy. So we're moving it both directions and sharing that energy. So, just to get into real high level steps in decision making around design of these systems, first and foremost, the foundation of every system, regardless if it's a standalone building or groups of buildings, is a thermal load profile. And getting that as accurate as possible, because that's really the key to understanding all the energy flows and what you need from your assets. So that's first and foremost, and I think we all know that. Next is really finding and selecting the right thermal assets. So in the past, it was just, we got this space out here, we can fit this many boreholes, and that's what we're using. Well, as we move into denser urban environments, as we move into very large campuses and tall buildings that need a lot more energy than what maybe is available on their site from a vertical ground loop perspective, we have to look at other thermal assets, what's available. And, then there, of course, there's always a cost matrix to that. We have to look at what is each thermal asset, is it available, how much is available, and what does it cost to get that thermal asset? Okay, and then we can do that analysis and really make the best choice. And maybe it's a mix of a couple different types. That's the best solution for the site. Then from there, you're looking at your distribution system, especially when you get into district systems, and whether it's a community, whether it's a campus, what is the best way to move energy around, to share that energy for the least amount of cost, the highest efficiency. So, we look at that from both a one pipe perspective, a two pipe. Those are both typically ambient systems. So whatever the ground temperature is, we're within, maybe 20 degrees of the ground temperature. So we call that an ambient system. Or we're going to a four pipe, which is, we're using some type of a central plant to deliver hot water, chilled water, to the district. Okay. And then from there, at the end, we're looking at heat pump technology. What do we use? What's the best? Well, it varies. It really depends on the project, the site, the building, or the campus. If it's a central plant, are we looking at chillers? What type of chillers? We have to look at the lift. What's the outlet temperature, the load temperature we have to supply on the hot water side? If we're including domestic hot water, that's all year round. So do we really want to put one heat pump in to deliver 130 even in the summer, when maybe we could be reducing that for just reheat only to maybe 95 degrees? So maybe we have a couple different types of heat pumps and how those get married together. If it's a single building, are we doing domestic hot water? Are we using distributed heat pumps for HVAC? Those are different efficiencies because of the load temperatures they're working under, the source temperatures they're working under. So, when you look at all these different technologies and you start to analyze that, number one, you want to look at efficiency, you want to look at cost, you have to look at delivery temperatures, you want to look at turn down and loading. Those are all really important factors in determining the best technology to use. But also with the tools that we have available today, it's really difficult to size ground loops, let alone multiple source technologies, and then multiple heat pump technologies in one platform. And what I'm going to show you today a little bit is what our company's been kind of moving towards, which is called Transys. And it's a very dynamic modeling tool that you can put in all the different components and all the different source energies, write dispatch models, and really model a true system in how it's going to operate. And that's really critical because, the ground loop tools that we have today for just a single building work great. If you're using a distributed heat pump only and you have a ground loop, fantastic. GLD, GLE Pro, they all work really well. But when you start mixing and matching different COPs and ERs of heat pumps, it doesn't allow you to break those out based on the load profile and how much each of those systems are putting into the ground loop or taking out of the ground loop at different times of the year. without a lot of, spreadsheet calculations and things of that nature. So, we need more tools, and I think those are going to come as this technology continues to grow, and the market is changing. Obviously, this is becoming a really hot topic. So I think we're going to see more, and better tools, out there, hopefully, that are coming. So first, let's talk about single building and multi-source energy systems. So this kind of, just a real rudimentary diagram, but this is really showing how we can be fully electric using hybrid equipment and also sewage heat recovery. And I'm going to show you a couple of examples of how exactly we're doing this. And a lot of times, depending again on that thermal profile, you may or may not need one or both of the hybrid boiler cooling tower. Okay, just depending on what that load profile looks like, what the building envelope is. If you're designing passive house, even in the northern climates, oftentimes you're going to be cooling dominant. So do you need that cooling tower as a hybrid peak shaving type of a device? Wastewater, remember, we can not only can we take heat off of wastewater, but we can also put heat into wastewater. Okay, so that can be utilized as a bidirectional thermal resource. So that's really important to understand. The heat pump technology on the domestic hot water side has really gotten better. The efficiencies are there. So you can electrify a building now, not impacting the total KW, peak KW, which is really important because we get into some of these very large buildings, which I'll show you. Certain rate structures from utilities will have major implications if you get over a threshold on your peak, that then they get charged a different rate, which can be very high. So we really have to look at, when we go all electric, what is that peak going to look like? How are we peak shaving? Are we using any hybrid equipment? And then one thing you can also add to this is thermal storage. If you're getting close to that peak on the electrical side, we can put in some thermal storage to reduce that capacity and have the ability to continue to heat and cool the building, even though we're running at part load condition. So by marrying all these technologies together, we absolutely can electrify these buildings. We can manage the peaks and not impact the electrical grid negatively, but we've got to get really creative, and we have to model these correctly because there's not a lot of tools out there to do that. So this was a project we worked on. It's still in the design phase. They came to us wanting to fully electrify this building. And this is a very tall building. It's over 60 stories. They've got 10 stories of commercial and mixed use space. And then it's all resi up on top. And they were going to go in initially with electric boilers to electrify this building. And they came to us because they were getting over that 1 megawatt peak. And the power company then, for that 5 hours a year, they're going to be over that peak, was an astronomical cost to them. So that wasn't an option. So they still want to go fully electric, carbon free, but how do you do it? Now, this is a condominium, a high-end condo building. So it's actually a central plant. It's not a distributed heat pump system. So we have a chiller. They had a chiller and a boiler plant to serve this building with hot water and chilled water fan coils. So we started diving into this. And the first thing we looked at, okay, what's the footprint? You can see there, not very big for this size of a building. Maximum number of bores we could get, depending on spacing, was 70 to 80 bores. Typically in this market right now, the depth for most ground loops we're drilling to 850 feet. We started to look at even maybe what if we go to 1,000 feet? What if we use, maybe some better technology in the ground to get a little more heat extraction, rejection, like maybe a concentric heat exchanger, something of that nature. So we evaluated a lot of those. But then what else we evaluated was thermal storage, and then also some air source heat pumps. So I'll just kind of give you a real rundown here. This is the baseline. So a electric boiler was 9,300 MBH, which is a very large electric boiler, and an 800-ton dry cooler. So then we started looking at, okay, let's throw some geo in here, maximum amount, 70 bores. Let's take the domestic hot water off and just leave that on, the boiler system. Well, guess what? We weren't able to do a lot with geothermal. Annually, we can do, 57% in heating and 76%, but the peak is the big part. And we were still needing a boiler of around 8,300 MBH for the peak, which was really, difficult again to stay under that 1 megawatt from a power perspective. So then we looked at adding the domestic hot water, because if you look at the thermal profile here, it's pretty balanced. Can we help on the cooling side by adding domestic hot water and using heat pumps instead of electric boilers? So our boiler did come down slightly. Our dry cooler came down, went from a wet cooler to a dry cooler, and we cut that in half by putting the domestic hot water heat pumps into the mix, because now we're using that waste heat from spring to fall, pulling that off the condenser loop side of the building and putting that right into domestic hot water production. And then we looked at, okay, what can sewage heat recovery do here? This is obviously a residential building. We've got a lot of wastewater. We started putting in some sewage heat recovery, again, both from a heat rejection, heat extraction component. And now we're down to, we shaved another 500 MBH off the boiler, and we were at about 400 tons on the cooling side. So again, we keep whittling away at the conventional equipment by adding more technologies. Now, doesn't mean cost-wise that that's going to be the end result, but from a theoretical, application, what's the best we can do? These are all this, technologies that we started to add in to get to where we wanted to be. And then the last thing we did actually, and I don't have a slide here, is we added thermal storage. And thermal storage was the biggest component to getting this basically to eliminate both the boiler and the dry cooler, other than maybe some redundancy for backup. Okay. But thermal storage was, I think it was around 3 million gallons for both a hot tank and then another 3 for a cold tank. Now you start looking at, where do you put that? Okay. If you're taking up parking spaces, if you know anything about the Toronto market, I think a parking space goes for $65,000 to $85,000. So you take up 6 parking spaces, you have to work out that cost benefit of removing parking and putting in thermal storage. So there were a lot of things that are going on with this building, but we were tasked with, first of all, is it even possible to get to carbon-free, fully electric without getting over the 1 megawatt in energy? And we were able to actually come back and show them that we could do that. Again, with thermal storage. So the last iteration I had on here, we were down to about 2 megawatt in with the 70 bores, domestic hot water, sewage heat recovery. So, but we're saving, a ton of energy overall in those scenarios, over 50% in total energy with geothermal, domestic hot water, and then sewage heat recovery. So these were, again, I mentioned we gave them a lot of other options. They can, reduce their ventilation, reduce their domestic hot water load, look at thermal storage, which we did analyze. We also looked at possibly, because this is a hot water, chilled water, we could use an air to water chiller to do some hybrid during the spring and the fall to help take off some of that load. And then also we could maybe charge the loop field to give it more capacity during the peak times using that air to water system. And then of course their envelope is always a really big component to reducing load. So those are all of our kind of options for them. This is another project in New York City. Again, 100% carbon-free, all electric. It is a passive house design, distributed geothermal heat pumps throughout with domestic hot water heat pumps, and then sewage heat recovery. So that was the design intent. And when we started looking at this, it was interesting because we were using traditional tools in the marketplace to design the geothermal ground loop. And we really just didn't feel comfortable with where the results we were getting. And then we started to look at Transys and go, okay, because when you add sewage heat recovery and we can use that as heat rejection, heat extraction, how does that really impact the system? And, GLD or some of these other tools just they don't have that capability. So then you get into a lot of manual calculations, and we needed something a little more dynamic that was hour by hour, that we could really look at, how does all this work together? And one thing about passive house, like I mentioned, you absolutely go to a cooling dominant profile. So if you look at this thermal profile of this building, the domestic hot water load is almost equal on a peak basis as the heating load. And we're we're 3 times as big on our cooling load. So when you think about that sewage heat recovery, you're not going to take a lot of energy out of the effluent because you just don't need it. We need to put it into the effluent and as well as the ground loop. So we didn't see as big of a reduction in our ground heat exchanger by adding sewage heat recovery because we just don't have the heating load. Okay. We actually did a little analysis where we just took the cooling out of the equation and the sewage heat recovery system did 100% of the heating. The problem is that's not reality. Reality is we have a tremendous amount of cooling. And when you add that in to the system and look at your long-term effects of the ground loop, we have to be very careful in how you size that. So, we can maintain a healthy system over time. Again, this is an urban setting. It isn't a parking lot, not under the building, but still very difficult to install. And you don't want to have to go back in and make repairs or something or add loops down the road. As a matter of fact, you really can't because we're taking up about the entire parking space. And this is just kind of our Transys piping layout. So we had, on the right-hand side here, we have our domestic hot water part of the system. The green area is basically your building system. This little box over here on the left is your sewage heat recovery. This is the heat exchanger device. And then this little box down here is our ground loop device. And then this is just your piping network and pumps and basically how it all gets connected. And then we can write dispatch models based on temperature profiles and limits of each of these systems on how it should operate. And then we can run that and simulate exactly how all this works together. And if we can meet domestic water demand, if we're meeting the building demand, what are we doing to the temperature in the wastewater tank? What are we doing to the ground loop? And how that works throughout the year and over 10 years. So a few things that we have to put into the program. Obviously, you need to know your daily domestic hot water and wastewater availability. That's critical to sewage heat recovery, right? We need to know what that looks like. Again, there's a lot of information out there. New York City, from what I understand, what we were modeling initially was not close because even though they have occupancy codes, they tend to put more people in these buildings due to rent costs than what you're actually by code designing to. So we did a lot of sensitivity there and looked at that. And then we run the system, and this is really telling you what your utilization is. So if you look at the flows, we look at the orange, that's our ground loop. The blue is your building, which is matching your ground loop. And then the yellow down here at the bottom is the utilization of the sewage heat recovery. This is more on a monthly basis in August during the hottest part of the year. And then this is on a yearly basis. So you can see here that we're actually, which was really surprising, is that we're really not utilizing it in the wintertime. Now you could turn it on more in the winter and turn your ground loop down, which is, some of your controlled dispatches. But what you really needed it for was for cooling. We need to be able to reject heat to the sewer as well as the ground loop in order to reduce any bores. And so we went from about 128 bores on this site to 95 bores by utilizing the sewage heat recovery system. And again, the only way you're going to find this information out is to really have a dynamic program that can model all these systems integrated together, and we've learned so much from this because it's, when you look at just, static temperatures, one thing that we put in here as well is we started to change the effluent temperature because we all know, you brush your teeth in the summer and you brush your teeth in the winter, your supply water temperature changes, which means when you mix it with the domestic hot water, your effluent temperature changes from month to month, throughout the year. We were running initially a static 70 degrees. Well, as we did more research and looked into that, it actually gets over 70 degrees in the summer, which didn't help us. That actually hurt us. But in reality, we want to be as accurate as possible, right? So this is what we're trying to do. And by utilizing these technologies, now we can save costs in certain technologies by adding, a different technology. Yes, there's cost to that as well. Then you run the cost benefit. But first you have to know how it works, right? How do you size it? How does it all work? What is your real reduction in your initial technology, your geothermal system? And then you can start playing that game. And this is just ground loop over the years. So the dark blue is the first year, and then the light blue is after 10 years. And then the one on the left was 98 bores or 95, and the one on the right was 128. You can see they didn't change a whole lot, but they did change slightly throughout the year. But we're modeling this But as you can see here, this is very cooling dominant. We never get below, 45 degrees, but you can't reduce your bore field anymore because we're hitting that 90-degree mark. So now if we could take care some way to take care of those couple of hours on that peak, obviously we could probably shave another 10 bores out of the system, and just handle that peak differently. So those are, again, some of the things that this really helps show you, very detailed how I can manage my system and try to reduce costs. This was the wastewater storage tank. So we're modeling that. And you can see we're not using it in the winter. We're using it pretty much strictly in the summer to get rid of heat. And then this was on the right, our domestic hot water profile. We're showing the storage tanks, the set point, delivery temperatures, and making sure that with this system, we can deliver the proper temperatures throughout the year. And again, this is just that utilization schedule and energy source and kind of showing, as a total, how much energy are we getting out of the sewage heat recovery? So, we need to know that, because if we're going to invest money in these technologies, how much energy are we getting? And so that goes back into your cost model, and then you can go through that exercise. Another technology that's really starting to, I think, become really prevalent, again, especially, I think the manufacturers of these heat pumps, which is an air to water and a geothermal heat pump built into one. If you were at the ASHRAE show, if anybody on here was at ASHRAE last year, there was at least a half a dozen large manufacturers of this technology that are getting into the space because they see this as becoming critical to decarbonizing major metropolitan areas. There's no other way to do it with just, geothermal or ground source. There's not enough space. Most of these buildings are existing. So, how do we do this in a way that we can use both air when it's effective and ground when it's effective, put that together and provide what's needed for the building. And so this was the very first building that's done this with a chiller that is designed to do both of those things out of the same box, basically. So it has a air coil and a water coil that it determines what's the most efficient method, and then heats and cools the building, with that. It was serial number 1 from the manufacturer. So it was the first of its kind from that particular manufacturer. This building was more than 45% LEED platinum. It was a new building, so it was a tear down and rebuild. It's an energy pile project. So they had caissons, I believe, down about 150 feet or so. And they put 3 loops or HDP U-bends within each caisson at 150 feet, concreted. And then that's the thermal ground source. And then, of course, we have the air source. And, all of these chillers have to sit on the roof because of the air source component. So the entire roof space was used up with the heat pumps. So there was no amenity space on the roof. It was all mechanical space, which is unfortunate, but it is an office building. So that worked fine for what they were looking at. This just got commissioned and is in operation in New York City. And it's a really exciting project because I think this is a really great model for this technology to show what capabilities are in even places like New York, where air can still be a very viable thermal resource at a lot of different times during the year. All right, now let's move into thermally connected and shared energy systems. Now this is where we're putting multiple buildings that are not connected to one another on the same piping network and then sharing energy through that piping network. So, if any of you sat through any of my presentations in the past, we've talked about, why are we looking at doing this? There's a lot of pros to it. There are obviously some negative impacts to it as well. Those all have to be weighed. But I think the biggest benefit, number one, is load sharing, especially if you can have a diverse set of buildings from a thermal energy profile. Okay, so if, let's just say hypothetically, you had a data center down the street from 50 homes. You've got a lot of waste heat. You've got, in the northern climate, you've got a lot of heat needed. We can utilize that. You still have to have that data center during the middle of the summer be able to get rid of heat, not putting it into the loop. But things of that nature, when you can load share, convenience stores, hospitals, a lot of these different buildings that have a lot of heating and a lot of cooling would be really beneficial to these type of systems. Then also the big benefit is you have a much wider area to try to go and grab other sources of energy, waste heat, sewage heat recovery. Maybe there's some surface water nearby. You can distribute smaller vertical ground loops into smaller areas versus having to try to find one large common area, possibly even in the street, which has been done. So you have a lot more options and flexibility with these systems and where you can get that, that energy source in using different types. Okay. And then the biggest benefit, I think, overall is that we're now looking at a new thermal network that is attractive to potential utilities and or private third-party owners. And that's really, I think a lot of people that have been involved with IGSHPA and been to different conferences, been saying this for probably 2 decades. When the utilities get in and they can amortize things for a much longer period and a smaller rate of return, spread that cost over an entire rate, base versus a few people, it becomes much more attractive from a cost perspective. Even if the cost is higher to install, when you can look at it from that perspective, it dramatically changes your cost structure. And so that's really critical to these systems because you're now seeing that actually happen. Utilities are paying attention. There's a few in New York and in Massachusetts that are putting these systems in, doing pilot projects, and it's really changing the landscape on community geothermal. Of course, the downside is there's more cost, right? You've got a lot of interconnecting pipes, infrastructure, you've got more pumping horsepower overall to move that energy. So there's some parasitic losses there, reduces your overall system efficiency. But that parasitic loss is on the infrastructure side. Whoever's owning and operating that is bearing that cost, not the end user. So the end user doesn't see that efficiency loss, directly. Okay. So, but it is there. All right. Space could be an issue depending on if we're talking about downtown, New York, or if we're out in the suburbs of a city, of course. And then, logistics, operation, maintenance, right-of-way access easements, all those things, that's all new. Those things are being worked out. Thankfully, now there's some precedents that's happening that people can look to and go, okay, let's talk to them. They've done this. So just real quick, a couple of different models that are out there. I think a lot of people are familiar with the Whisper Valley project. The Whisper Valley project would be very similar to the one on the right, where you have a vertical borehole per home, and then you have what they call an energy transfer station or a heat exchanger, and then you have a district loop that connects things, and then you might have a couple of central energy sources, whether it's vertical ground loops, cooling towers. Whisper Valley, it's a cooling tower. And that way, with the energy transfer station, less risk of if somebody, accidentally did something within their own home, it's not going to impact the entire system. Obviously, the one on the left is just individual boreholes. Certainly from a cost perspective, very attractive, but from a utility model and a third-party ownership model, not as attractive because there's, the infrastructure, the things that are attractive for utilities to own and operate, it's not there. This is all on private property. And so just not as attractive from that perspective. And then the other two models that are out there, a little bit more centralized from a energy source. So we don't have any direct energy sources on private property. All the energy sources would be located somewhere else. So either in the street or in maybe a park or, some type of a right-of-way, in their distributed energy sources. Again, could also add in sewage heat recovery here. You could add in another central pumping station that maybe has a cooling tower or, a boiler or something of that nature for either backup or hybrid. And then you can see the little black boxes still having that energy transfer station. Again, that's a little bit more of a de-risk scenario. So you're de-risking your infrastructure from your building. And then the one on the right, the only difference there is you've just taken out the energy transfer station. So now everybody's getting the same fluid, the same pressures. And so you have a little bit more it's low risk, but you have a little more risk of potential leaks impacting, from inside the building for the whole entire system. And this is an example of one that's been done. It's been in operation now for over a year. This is up in Canada in the Toronto market. There's 312 homes, about a little over 2 miles of 6-inch main single pipe ambient temperature loop. There's 4 pump stations to pump that loop. There's 11 vertical pods, if you will, of distributed vertical loops around the site to inject and reject energy in specific locations. And it's been working great. Obviously, we started out initially with an aggregate thermal profile of the entire site. We had to do a lot of sensitivity analysis, because when you're building new, what happens if they don't build the building like you've modeled, right? That's always a question. And who's verifying that? So great thing is they have a program there similar to like Energy Star, where they do go out and test, building envelope inspections, blower door testing, thermal imaging. So they're really making sure that when they say they're going to build a building to this performance level, that they do it. But we did a lot of sensitivity on that, because that can greatly change the scenario here, right? How your system performs is really dependent on that. We don't have any existing utilities to go back and go, okay, let's reconcile that with our model to make sure we're close on how these buildings perform. So that's one thing that you really should do on most of these projects, is a sensitivity analysis. And then, of course, we ran our Transys model, which again is really key to these types of designs, because we need to model that ambient temperature loop, and we want to know the temperature between each building and each injection point of energy along the way. So we know that, one customer isn't being penalized for being in a certain location versus another within that ambient loop. And our goal was on this project to maintain a minimum of 5 degrees between any energy source. So, we had 20 to 30 homes between each section, and every home was going to get within 5 degrees, which means on their utility bill, if they walked down to their neighbor and said, "What's your bill?" "Well, mine's, $100 this month. What's yours?" It's not going to be drastically different. They're going to compare them, and they're going to be almost identical. It'll be more based on living habits than it would be on, how the system was designed. And this is just some of the highlights on the infrastructure. Everything in this particular site was buried underground from an infrastructure, all in the street right away. So, from a utility perspective, they had to have all the easements and access agreements, et cetera. This is very critical where we place these, so you're not blocking people's driveways if you actually had to get inside. There is some implications with confined spaces, so you have to make sure whoever's owning and operating has all that training and so forth. And so this was quite a challenge, but it all worked out in the end. So these are some of the pictures from the actual site. This is down inside one of the vaults with the pump. This is a vault getting installed. These are some of the pedestals that were above grade. Obviously, all your electrical is above grade. The only thing we have that's electrical down inside the vault is the motor itself and the control sensors. All the VFDs and the breakers and control interfaces were all above grade in this pedestal here. So, all right, let's look at multi-source thermal networks and the 5G, kind of what NREL is determining is the 5G ambient temperature loop. And this is where now we're taking that same concept of, we're going to share energy between all these buildings, but now we're going to start using some other sources other than just geothermal. This was a project we did the concept design. It has moved forward in design. We're not actually part of that process. This is in New York as well. This was a multi-phased approach. A lot of geothermal ground loops, obviously, but we did also include building level sewage heat recovery. And so as we went through this entire concept design, we started looking at all the different ways we can save energy. And they're doing a lot of solar, obviously, on the electrical side. But we're also, we had a baseline, we had an all electric model, we had the geothermal model, then we had the geothermal with sewage heat recovery. And so you can see there that we saved about 8% more energy or dollars, I'm sorry, no, KW, over the just straight geothermal system. And again, this was not utilizing a, municipal main. This was just at the building level before it leaves the building. And about 5% in emissions by incorporating sewage heat recovery just at the building level, because there was a lot of multifamily buildings there, a lot of apartment buildings, 4 to 6 story apartment buildings and a hotel. So we looked at that and, added that into the mix to, again, reduce emissions, reduce costs, increase efficiency, and also reduce boreholes. I don't remember how much we reduced here, but it wasn't significant, but there certainly was savings in the capital cost of the ground loops. And if you go back to this drawing, there were some limitations, especially on the first phase with these parking lots, on how many bores you could actually place before you get into the next phase. So we had to reduce energy so we could make that all work. So that was really an important part of that project. It's another project in New York. You can see we do a lot of work in New York because New York is kind of leading the country right now with decarb and geothermal activity and incentives. So there's a lot happening there, and hopefully more states will look to New York and start to emulate, how, their success and what they've been doing to drive this technology. So this is another campus. This is a single owner campus. There's about 65 buildings. You have basically what we call staff housing down here on the bottom left. You have a bunch of residential homes. They're kind of like homes, but it's housing with all the orange buildings. And then you have the large green commercial buildings, which are schools and admin buildings and athletic building on this campus. This is sitting up on a very high point along the river. So you basically had, bedrock at surface or within 10 feet of surface. So, trenching, installing piping externally for a district system is very challenging. And so the single pipe ambient kind of made the most sense because we could reduce costs in piping and trenching. Number two, we wanted to thermally connect all these buildings because you have a lot of diversity here. You have, people moving from these buildings to the commercial buildings throughout the day. You also have different load profiles because you have computers and staff and you have a swimming pool in building 13. So you have a lot more cooling load in those commercial buildings, a lot more heating load in the residential buildings. And then of course, with the staff, they move to and from again throughout the day from their housing up to the other housing for the other people on campus to do schooling and so forth. So we wanted to try to take advantage of that diversity. And there was a significant savings in bore field cost by interconnecting all these buildings. So again, got to go through the thermal load process, develop an aggregate, put that, and then figure out your groupings, figure out where you're going to put your thermal resources, what's all available, and what's the strategic locations for those to make sure that we can balance out our ambient temperature loop and everybody's, kind of getting the same temperatures, okay, for efficiency. Even though this is a single owner, we still want to try to maintain that, 5 to maybe 10 degrees would be a maximum between energy sources, because we don't want to get to a point where heat pumps are getting close to their operating limits. So we need that buffer. And, all this modeling, we're using average weather data. So you need a buffer in your design parameters to make sure if you have an extreme weather event, we're going to get through that without, hitting the bottom end or the top end of our operating limits with our heat pump systems. And so these are distributed heat pumps in all these buildings, no central plant here. And then we also looked at all these buildings have an outflow point right here on site with their effluent. So we gave them an option and looked at the reduction in bore field to put in a sewage heat recovery station on the main leaving the site. And we can inject that right back into this ambient temperature loop, and we could remove I think it was this bore field here that we could remove that almost entire bore field by putting this station in here. And we'd have to move a couple connection points around. But this is another, single pipe ambient temperature loop application. And we went through, again, all the Transys modeling. We show, again, the profile of the temperature loop shows exactly where every time we inject energy, what happens to the loop. Then we go back down as we hit all the buildings. This is a heating dominant profile, although somewhat balanced, but because of the ground temperature, we're still kind of heating dominant. And so we ran this here in the middle of winter, and you can see our lowest point, we got down to about 39 degrees, and then we climb back out, and then we come back down. So we could technically take a few more bores off of this bore field here and let this drop a little further. And again, over the long term, what does that sine wave look like? Is it going to build heat, et cetera, over time? The nice thing about distributed energy sources is that we don't have one large grid of vertical loops, where then you do really have to look at long-term net effects of heat buildup, because we've got so much of this distributed around site. We have a lot bigger area we're pulling energy from, putting energy in. So we don't have to look at that as, a 30-year scenario, because you're not going to build heat in these like you would if they were all close, together in one bore field. And the last part I'm going to look at here is just then from a campus central energy plant perspective. So we'll take a look at that. This is the easiest design and scenario where you can start to integrate lots of technologies, because you have a central location with your heat pump system. Now I can use a lot of different sources to bring energy in, take energy out of that central plant. I can use a lot of different electrical technologies to produce the electricity. I can use thermal storage. I'm generally putting up a new building. A lot of the campuses we're working at, we're putting up new buildings to house this equipment. Thermal storage can be, near that central plant. A lot of them are built to sit outside. Some of them are inside buildings. It just depends. And then again, finding those other assets. Is it surface water? Is it, air to water, air source technology? Is it sewage heat recovery? Could it be maybe even some CHP, rice engines? We're looking at all these different technologies to deliver the most efficient and cost-effective solution. And then, of course, we've got hot water, chilled water distributed out to the campus, removing steam, removing gas and fossil fuels, and doing this with all electric. One of the things that we've done recently on a lot of projects of this nature is add thermal storage. Thermal storage has huge impact, both from a rate structure perspective and what they're paying on those peaks, but also to a reduction in ground loop, which is your largest capital expenditure when you're talking about thousands of boreholes for these campuses. So you can see here, when you add thermal storage, we flatten that load on our system. We can reduce overall capacity and CapEx because we don't have that huge peak. Same thing with heating. So, that is two different tanks. We're not putting in one tank and flipping that tank. It's a hot tank and a cold tank. Most of these campuses have heating and cooling happening year round between reheat, domestic hot water, and then even in the middle of winter, most of these campuses with labs and so forth, we've got some chilled water and some cooling in interior spaces. So they're running in simultaneous mode almost all year round in these large campuses where we've got central plants, which is, effectively doubling your efficiency on your heat pumps, going as much as we've seen as high as 10, but on average around 6 to 7 on a COP basis for simultaneous mode. And that's where selecting the right chillers for the right application is critical, because you've got to look at that lift, you've got to look at your turn down, and you've got to look at, the efficiencies at those different temperatures, especially when you're doing, geothermal. Are you going to put glycol in the system? How low are you going to go on your source energy? Is everything mixing? Is it not mixing? So there's a lot of questions and a lot of design, decisions that have to be made that have cost implications. It's really critical to your master planning and into your schematic design. You got to get to those yes and no's real quick, so you can start to weed out the technologies that don't make sense and get to the ones that do, and proceed with that design. So, but these are all out there. They're becoming more and more readily available, and we're seeing a lot more of this out there. So it's really great. We can make things a lot more efficient, a lot lower CapEx, and really low maintenance, which is critical to these central plants. Most of these are all dark rooms. There's no 24/7 staff. It's, there's a computer basically running it, and people are just monitoring it, and it sends you, emails and texts if there's a fault of any kind. So yeah, all dark rooms. So the last project I'll show you here is the Epic Corporation, which is the largest geothermal system in North America. A lot of people don't know about it. It's in Wisconsin. It's a brand new campus, so it's all greenfield. It started 15 or so years ago, maybe more, and has expanded and expanded and continues to expand today. They're always adding new buildings. We're always adding onto the system. Right now, currently, there's over 9 million square feet. There's 40 plus buildings, roughly 27,000 tons of heating and cooling, 100% electric, 100% geothermal, as well as solar and wind generation on site. And they have their own data center. I'll kind of show you here a little bit about how it's all laid out. They have a data center that's underground, that's up here in this building up here. It's an underground data center. The data center is actually passively cooled with the geothermal water. The geothermal loop and the ambient temperature never gets above, I think it's 78 degrees. And so we can passively cool a massive data center without any active compressors, which is phenomenal. You can see there's multi-source energy here, but it's all geothermal. So we have a quarry, so that's an open loop system. We have multiple vertical loop systems in the green. And then we have this large retention pond that is a horizontal pond system. All of these interconnect with the ambient loop. The ambient loop then injects into a bunch of central plant pods that serve, anywhere from 5 to 8 buildings. And so as those 5 and 8 buildings share energy in the central plant that serve those, when it gets out of simultaneous mode and you either need more heat or more cooling, then it takes off of the ambient loop. And the ambient loop, I believe, is a 36-inch pipe around 80,000 gallons a minute at its peak. So it's a very large system. They do snow melt here as well to help balance and get rid of heat, because this is a cooling dominant, even in Wisconsin, 100% cooling dominant with all the office space and data center and et cetera. So they're always getting rid of heat. And as we know, this surface ponds are tremendous at getting rid of heat. The quarry is tremendous at getting rid of heat, much better than our vertical bore fields. And they started with vertical bore fields, and those are still being used today, primarily to maximize space, because they're doing other things over top of the bore fields. But and there's been a lot of research at this site. The University of Wisconsin-Madison has done a bunch of research about, how is this site impacting ground temperatures, groundwater? Where's the heat going? Is it impacting water wells downstream underground? And what they found after, a lot of testing is that you get outside of any one of these vertical bores, 50 feet, 100 feet, and the temperature's back to the mean ground temperature, which is amazing. But again, they're not superheating this ground. They're only getting, they're only running 78 degrees as a max temperature. That's not a typical system where you might see 90, 95 degrees, 100 degrees into the ground. So performs really well. Impressive system. This is kind of some of the site. This is the quarry up here. This is their solar field. And so they did geothermal underneath the solar field first with vertical ground loops, a vault, and then did all the network piping and then put this in over the top. So they're kind of, getting dual work out of that same space on campus. And that's it. And it's 11:35. I did pretty good. Wasn't sure I'd get through all that in an hour. So thank you. And we'll take questions.
All right. Thanks so much, Brian. That was a great presentation. I especially love those graphs. Lots of great data there. I want to be respectful of everybody's time. As you mentioned, it's 11:35. Do you have time to stick around for questions?
Sure. Absolutely.
Okay. Great. We have a lot of questions here. So we'll start with the first one here. And certainly appreciate your time today. If you need to jump off, we understand that, and this will be recorded and put on the IGSHPA website. So if you can't stay around, you'll be able to hear these questions. First question comes from Ruben. He asks if there are other modeling tools than Transys worth looking at. There's some modeling tools emerging like ComSoft and IVs.
Yeah, I'm not familiar with a lot of the other software tools that are out there. I know there is another similar software to Transys that's available out there, and I know that the DOE and NREL is working on their, is it Urban Opt software? Now that's not going to be a detailed design software, but certainly from a high level, maybe, feasibility study, concept design level, they're working on that. That, at least from my understanding, is there's not a lot of options other than Transys Ultra on the market. There might be one or two, but I'm just not familiar with them.
I take it that's because of the complexity of the calculations.
Yes.
Jack asked the question, does injecting heat into the wastewater impact the effluent that is exiting the building?
Well, yeah, it will exiting the building, not in a great degree. So we'll set like there'll be a sensor in the tank, and the tank will have an upper limit on the tank where the system would then shut off. And then as more effluent flows in, it'll cool it back down and flows out. And generally, that might be around 100 degrees as a maximum temperature. Obviously, we're not going to get much hotter than that because our ground loops aren't going to run hotter than that. So we wouldn't really ever see temperatures warmer than that, but you could. From my understanding, talking with a lot of municipalities, the upper limit in a lot of places is anywhere between 110 and 140 as far as their upper limits before they might have any issues with, microbials or bacteria or stuff like that. But yes, we do set an upper limit. Now, once that goes downstream and mixes at the street, depending on how big that line is and the flow in that line, you're probably not going to see any difference once you mix at that point. But leaving the building, certainly you're going to see some temperature change.
Okay, good to know. That's fascinating. Andy asked a question, and Rose answers the question. So I'll run this by you since this is recorded. That way, the answer will be on the recording. What size? Andy asked, what size was the sewage storage tank? And Rose answers, we modeled a few different tank sizes to optimize it. For the building Brian showed data for, we modeled 20,000 to 30,000 gallon tanks. When we increased the flow rate through the Shark system, we increased the tank size. Any comments on that, Brian?
Yeah, right. I mean, I think the optimized tank size there was 20,000. If you look at the cost benefit side of it, we tried to see, can we get more energy? How many more ground loops could we reduce if we upsized it and upsized the flow? And it was minimal impact by going to, a 30,000 gallon tank. So, and when you're talking about a wastewater tank inside a building, every 10,000 gallons matters from a cost perspective in space. So, yeah. So the design will end up being 20,000.
Big tanks. Yeah. Thanks, Rose, for answering that. Well, right. John asked the question, don't you think it's possible the pumping energy for the overall system could be low or lower? If a bunch of buildings are sharing energy, we might not need to pump through the big ground loop. We might need fewer boreholes to pump through because of the diversity and storage aspects of the network piping. So through design and building selection, I hope it's not always more pumping energy. Yes?
Yeah, I would agree with that. I mean, what I was speaking to, I guess, is your overall horsepower, peak horsepower on a design day. Absolutely. If you looked at it from an annual perspective, my guess is he's right on that you're going to end up with less if you have a very diverse load profile and you have a system that is sharing energy. Yes, because a lot of times you're going to have most of those ground loops running at minimum speed. The ambient loop will probably be at minimum speed. And so now absolutely your horsepower during those conditions would be much less.
Very good. Victor has a similar question that we had earlier about Transys. He asks about Polysun, Modelic Energy Plus. Are you aware of evaluating any of those systems?
I haven't personally. I'm aware of. I don't know that eQuest does that. I guess that would be news to me if eQuest can model something that dynamic. Maybe it can. I don't know about the other two.
Okay. All right. Very good. Michael has a question here that started some conversation on chats. This is always great to see participation here. He says, I understand flushable wipes create big problems for wastewater treatment centers. Have you experienced issues with flushable wipes and other solid materials plugging systems? Ruben comments that modern wastewater heat recovery systems focus a lot on solid screening, and the chopper pump / screening systems are designed to address this. Rose also commented on this. Yes, the Shark wastewater heat exchange system includes a macerator as part of the system. Plus, the system reverses the direction of flow periodically to help flush out the system and keep the heat exchange surfaces clean. Any comments on that, Brian?
Yeah, I will say again, and that would be technology specific. So Rose mentioned the Shark. The Shark macerator does not like flushable wipes, and I know that from because I know the people at Shark very well, and that has caused some issues over time. Now, if you look at some of the other technologies out there like Ureg and Huber, they don't use macerators. They don't chop solids. They actually have the solids flow right through, based on how their technology works. So then that would not be an issue. So really, it depends on the application, the technology. So, those things would have to be very specific. But it's not that the macerators can't do it. It's, on the Shark systems, it's just, I believe that it might have an impact on the blades and the longevity of the blades over time.
Excellent. Yeah, there's always something to discuss in these kind of systems. Ruben has a comment and a question here. The concepts and approaches using the modeling and tech options is really impressive these days. Feedback I've had from some utilities and operators is actual operation and control of these types of systems is a challenge. They prefer to keep it simple despite the theoretical benefits. What is your experience with this, and what does our industry need to do to improve this area of knowledge?
Yeah, that's the other reason why we like Transys, because Transys, you actually write control sequences and we can directly export the dispatch models and give that to a controls contractor and say, this is how it operates. Which is really important because when you get into highly complex systems and you're trying to determine, when to turn on and off different assets, that's really, really critical. Now, on the single pipe ambient, if you're just doing, geothermal assets and you got building, heat pumps, that control sequence and model is so simple. You're just ramping a couple of pumps up and down based on temperature. So those from a utilities perspective, like the Eversource model or the pilot that they're doing, and the few other ones that are out there, the control sequencing on those is absolutely simplistic.
Excellent. Okay. Being conscious of time, it's 11:45 Central. Do you still have time here to continue, Brian? Okay,
yeah,
lots of questions here.
Yeah.
In fact, one question is related to that. Kevin thinks that we need a part 2 of this webinar. Is that something you're interested in?
Yeah, I think we could do something.
Okay, we'll keep that in mind for 2024 for sure. Jim asked the question, have you been looking into any of the salt-based thermal energy storage systems under development?
I haven't personally, but I know that our company has. That is a up and coming technology that, that salt-based offers a little more thermal capacity. So it can reduce tank sizes. So instead of just water, that could be an option. And I think that will come, down the road. There's other companies out there that are researching, phase change materials and a lot of different things to do lift of temperatures to try to get the hotter temperatures. I mean, there's a lot of this space is rapidly ramping to meet the needs of decarbonization. So I think you're going to see a lot of this types of technologies, out there, because in order to get off of steam or to try to create steam from some type of a renewable resource like geothermal, we're going to have to see that kind of technology come about, because otherwise you're just putting in electric boilers to make steam, because geo can't do it directly. So those technologies I think will come, and I think that there's already a lot of research happening on that front.
Excellent. Jackie, Bob, and Arlene make some comments here about simplicity and complexity of the system. You talked about that a little bit earlier. Anything else on that as far as moving forward with controls, training, anything along those lines when it comes to making sure that this is all well understood and planned?
Yeah, I mean, I agree with that. I think, controls, it really doesn't matter if it's a single building, a central plant, a district energy system, or community loop. Controls are always the biggest hurdle, if you will, or challenge, because when engineers write control sequences, it's in English. Then a controls contractor has to take that English and put that into a code and write that into code that it operates how it reads. And so there's a kind of a disconnect there that, maybe AI will fix that, but I don't know. But so there's kind of a disconnect there, and absolutely that, that should be a great training course, and that could be a training course from, all different aspects of the system. But the beauty of these systems is they are less complicated. They do have a lot less maintenance. Once you get them up and running, once they've been commissioned and the bugs have been worked out, which a lot of these systems, it takes a full year to tweak the control sequences to make sure they're optimized and working correctly and so forth. Once you get that done, it's really, you just leave it alone. You're just monitoring. That's all you're doing at that point, because there's nothing that really needs to be, changed on a daily basis, et cetera. Now, with a caveat of some of these campuses, they do have to ramp up chillers based on domestic hot water load, and that can change based on what's happening on campus. Like Miami of Ohio, I know, working with Doug over the years, that they used to have to, determine an hour or two in advance when they were going to have a big domestic water load and have to start ramping the chillers. And they would do that manually. But that's just touching a button in your computer. It's not, you're not, going over to the chiller and actually cranking a valve or something. You know what I mean?
Makes sense. All right. Rick comments that they are running a project at MIT to reduce complexity, and he's hopeful that they will be able to share that soon. Some other comments here. Rose mentioned that we chose Transys for modeling because of the flexibility and customizability of the program, so that we can model the system specific to the project. Ian mentions here, ever use a keel cooler for closed loop heat transfer to and from sewer water? I'm not familiar with that term.
Yeah, I'm not either.
Okay. All right. We'll have to
look at that.
Have to follow up on that one. And then finally, Arlene mentions that NYSERDA promoted a good diagram describing 1 to 5 generation district energy systems that DOE adopted in our community geothermal heating and cooling opportunity. It's based on Scandinavian 5G as well.
Great.
So really good conversations here. I could stay on this discussion all day, but I know we have other things to do. And I really appreciate your time, Brian. Thank you very much for everyone who has attended. We had a lot of good attendance today, and this recording will be up on the website here soon. Have a great day. Thanks, everyone.
Thank you. Thanks for having me.